So this lesson is on evaluating and graphing polynomial functions. So the first portion here, we're going to talk about how to how to identify a polynomial, what criteria you must have in order for it to be a polynomial, and how to evaluate them in two different ways. So a polynomial is a monomial, or the sum of monomials. And a monomial, just to review, would just be a singular term. It could contain variables with exponents, coefficients, but there's nothing being added or subtracted in there. It's just a monomial term where it's things being multiplied. So you could have like 1/2 x squared. You could have negative 3x. Those would be examples of monomial terms. Now, a polynomial is also the sum of monomials. So a monomial is just a specific type of polynomial, but another type of polynomial would be a binomial, and that's when you have two monomial terms being added together. So, for example, if you had, let's say, 5x squared minus 7, that would be a binomial. Or if you had negative 3x plus 2, that would also be a binomial. Or maybe you have x cubed minus 1. Those would all be examples of binomials, which are also a type of polynomial. And then there's also trinomials. And that would be when you have three terms put together. So it could be like x squared minus 2x plus 1. That would be an example of a trinomial. Or you could have 6x cubed minus x squared plus 7. That would be a trinomial. It's just basically three separate terms linked together with those addition and subtraction signs. And then, of course, polynomials can also have more than 1, 2, or 3 terms, but we're just going to lump those together as a generic polynomial and not give it a more specific term. No matter which type you're dealing with, a monomial, a binomial, a trinomial, or just a general polynomial, all of the coefficients must be real numbers. So you can have a fraction like this 1/2, you can have a negative, positive, but they have to be real numbers, okay? So no imaginary numbers with these coefficients, okay? Then the other rule is that the exponents must be whole numbers. So notice that my exponents here are all positive numbers, which means that they're whole numbers. If they're negative, they're not called whole numbers, they're called integers, so that wouldn't count. Now, even this one here, there's no number there, but remember, if the x does not have an exponent, it's really a 1, okay? And exponents, of course, cannot be variables. They cannot be radicals, variables, anything else other than just positive whole numbers, okay? So let's talk about the degree of a polynomial. So when you arrange a polynomial in standard form, which is really important, that's when you're arranging them in descending order from least to descending order from greatest to least, or from left to right. So if you remember back to like quadratics, you had like ax squared plus bx plus c. It's the same thing here, but we may have other terms in front of the x squared, like an x cubed, an x to the 4th, x to the 5th, and so forth. But it would always have to start out with that highest degree first, and then working your way down in order. Then the degree of the entire polynomial would just be whatever that largest exponent is in your polynomial. So for example, if you look at these ones that I have up top, these examples I put, so this monomial term right here, this would have a degree of 2. This one here would just have a degree of 1. This example, 5x squared minus 7, has a degree of 2. A degree of 1, this one would have a degree of 3. And over here we have a 2 and a 3. So it's whatever that largest exponent is. Now those degrees do have special names depending on what they are. So if we look down at this chart here, a degree of 0 is just called a constant because all of the x's cancel out. So if you remember, when you have an x to a 0 power, that just equals 1. So it becomes just a constant. There's no variable left. If you have a degree of an x to the first power, which you would just see as an x in your problem, that is linear, and it looks something like y equals mx plus b, or that slope-intercept form. If you have x to the second power as your highest degree, that is known as quadratic, and that is your parabolas that we were working on in the last chapter. And if you have x to the third degree, that would be considered cubic. Notice the highest exponent we see in all the terms would be a cubed. X to the fourth degree then is called quartic, and the way I remember that is 4 quarters equal $1, so that's my way to remember 4 quart, or 4 quarts are in a gallon. And again, you can have unlimited amount of terms here being strung together, but the largest one in this case was that x to the 4, which is why it's a fourth degree. Okay, and then one other thing to mention is that when you do have it in standard form, this leading coefficient here, that's that first number in front of the variable with the largest exponent. And just as we did in quadratics, that constant at the end is actually your y-intercept on the graph, which will be good to know when we're graphing. It'll be helpful. Okay, so let's practice this a little bit. So we have this chart on the next page, and we're going to decide whether the function is a polynomial function. If it is, we're going to write it in standard form, and then we're going to state the degree and the leading coefficient. If it's not a polynomial, I just want you to tell me why, okay? So this first one here, we have x squared, x to the fourth, and 7. So it's definitely not in standard form. But before I bother putting it in standard form, let me make sure that it is actually a polynomial. So I can see that all of my exponents here are positive whole numbers, so that criteria has been met. And the coefficients are real numbers. So this would, yes, be a polynomial. And this is actually a trinomial, right? Because there's 3 terms. Standard form of this particular problem, then, I would have to put my term with the x to the fourth power first, since that's my highest degree, then plus 3x squared, and then plus 7. So my degree type here would be fourth, and that is known as quartic. And of course, then my leading coefficient, once I have it in standard form, it's very easy to see. It's just that first term, which is -5. Okay, so let's look at the next example. So this one here, right away, I see that this exponent has a negative on it. So I know that this is not a polynomial, and that is because of the negative exponent. So I don't need to do anything else here because it's not a polynomial, so none of the other stuff is going to apply. Okay, the next question. First thing I'm going to do is look at my exponents. All 3 of my exponents are positive whole numbers, so that criteria has been met. Then I'm going to look at all my coefficients, and I see that they're all real numbers. So yes, this is a polynomial. And now I'm going to put it into standard form. Now this one also, because there's the 3 separate terms, it would also be considered a trinomial. It's still a polynomial, but that's just a more specific name that you can use. Now, to put it in standard form, we want the highest degree first, which would be this -9x to the 5th power. Just make sure that coefficient that goes with that x to the 5th and the signs stay with it. So notice the -9 is in front there. Then the next thing down in descending order would be this addition of the 6x cubed and then subtracting the 8x squared. So now my lead term here, which would consist of this -9x to the 5th, is telling me that this is a 5th degree polynomial, and my lead coefficient is -9. And then finally, number 4, if we take a look at number 4, we see this x here that's inside a radical. The only types of variables that you can have in polynomials are variables with exponents that are positive whole numbers. This is a radical. So technically, if you were to make this an exponent, it would actually be the 1/2 power, which is not a whole number. So this is not a polynomial. So as far as evaluating polynomial functions, there's 2 general methods. There's the direct substitution method, which is like the old school way of just plugging the number in for x and then solving it using your PEMDAS or order of operations. And then we're going to go over a new method that's called synthetic substitution. So the advantages to synthetic substitution over direct is that synthetic you do not really need a calculator for. Technically, you don't need one for direct either, but it's a little bit tedious to do without a calculator. The second advantage is in a couple sections we will get into polynomial division, and synthetic substitution is really like you're half of the way there with the division. It's a very similar process. So you get used to using it with the substitution. When we get to division, it'll make it that much easier. So first two, we're just going to review the direct substitution. So direct substitution is simply taking whatever value for x they give you and substituting it into the x's into the equation or function. So remember, whenever you substitute in, you should always use parentheses around that number that you're substituting in. So of course, this particular problem, we're putting positive 3 into all 3 of those x's. Now at this point, you would have to use your order of operations, parentheses, exponents, multiply, divide, add, subtract. And first thing I would have to do would be to do 3 to the 4th power. And I can do most of this without a calculator, but generally speaking, it's just a little bit quicker for people to type it in and get the answer that way. So if you do use the calculator for this one, you will get 98. If you do it by hand, you should get 98 as well. Now, just to show you what that would look like on the calculator, just in case you're not getting that and you want to see what you're doing wrong, if I enter this on the calculator, I'm going to do 2 times 3 raised to the 4th power, then minus 8 times 3 to the 2nd power, plus 5 times 3 minus 7. Notice I'm using my parentheses around every time when I substituted in that number. And there's my 98. Okay, so now the next example, we're going to do basically the same thing. This time we have 3 places to put that number in. And this time we're putting in a negative number. So I often find that people are more apt to make mistakes when the number that they're substituting in is a negative. It's just an extra thing that you have to be careful about. So if I were doing this particular problem here, if I were not using my calculator, I know negative 3 to the 3rd is negative 27. Then I would have negative 3 squared, which is actually positive 9. Then over here, 2 times negative 3 is negative 6, but I'm subtracting it, so that would make it positive. So now I have negative 27 plus 27 plus 6 plus 5. Those 27s cancel, and I get 11. Now, of course, if you're just using a calculator to do this, again, putting the negative 3 in the parentheses, raising it to the 3rd power, plus 3 times negative 3 to the, oops, I missed my parenthesis. Oh, dang it. Okay, try now. All right, this problem does not like me right now. Okay, so I'm just going to clear this out and start over. Okay, so negative 3 to the 3rd power plus 3 times negative 3 to the 2nd power minus 2 times negative 3 and then plus 5. And there's the 11. Okay, again, you don't need the calculator to do it, but it does typically make it a little bit quicker. All right, so now we're going to move on to synthetic substitution, which will be a little bit nicer because I won't have to keep going to my calculator because it's so much easier than doing the direct if you're not using a calculator. Okay, so the first thing that you have to do here with synthetic is write down all coefficients in order from the highest all the way down to the lowest, okay? So we'll notice here we have x to the 4th, x squared, x, and then you have your constant, okay? So what's going to happen though, if you'll notice that there was no x squared, or sorry, x cubed in there. So if you're missing a term, that means that the coefficient was really a 0. So your coefficients are going to be 2, 0, -8, 5, and -7. So the first thing you want to do is write all those coefficients down in order. So the x to the 4th coefficient is 2. The x cubed coefficient is 0. The x squared coefficient is -8. The x coefficient is just 5, and then our constant is -7. And then the number that we're going to be substituting is over here in the front. So now, once you get that down, that's pretty much the hardest part, because the common mistake is that people will sometimes miss a coefficient, and then that will mess up your whole answer. So once you get your coefficients down and you have the number you're substituting out front, it's simply just addition, multiplication, and you're just going to kind of repeat that addition and multiplication pattern until you get to the end. So you always start out by taking that first coefficient and dropping it down, and then you multiply that to the number in the front that you're substituting. So 2 times 2 is 4, and you put that answer in the next column. Then you add up that next column, so 0 plus 4 is 4. Multiply it to the number out front, 4 times 2 is 8. Write down your answer, add up that next column. 0 times 2 is 0. Adding up the next column, I get 5. 5 times 2 is 10, and I add up that next column, and I get 3. So my answer here would, okay, so now that we got the answer is 3, let's check our work using direct substitution. I'm not going to do this every time, but at least you can see how it would work. So I would have to plug this 2 in for each of my x's. So it would be 2 times 2 to the 4th minus 8 times 2 to the 2nd plus 5 times 2 minus 7, right? So that's what we're going to be plugging in. Okay, so 2 times 2 to the 4th power minus 8 times 2 squared plus 5 times 2 minus 7. And notice I get the same answer of 3. So direct substitution, you can just use your calculator and get that answer. However, like I said, the advantages to synthetic are that you don't need to go to your calculator, and it will help us in some other things we're going to be doing in this chapter. So if you don't learn it now, you're going to have to learn it later anyway. Okay, so moving on. So we're going to do a couple more of these examples. So first thing you want to do is fill in all of those coefficients. So I have a 3 and a -1, a -5 and a 10. However, it looks like I'm missing both x cubed and x squared here. So I'm going to have 2 zeros for those two filled in as well. So in descending order, 3, -1 for the x to the 4th. Then I have to put a 0 for x cubed and a 0 for x squared. Then my -5, and then my constant of 10. My number out front is a -2. So now I can start doing my synthetic pattern where I drop that first number down, which in this case is a 3. Every time you drop a number down here, you multiply it to the number out front. So 3 times -2 is -6. Put the answer in the next column and add them up. Multiply those two numbers there, I get 14. Add up the next column. -2 times 14 is -28. Add up that column. -28 times -2 is positive 56. Add up that column. 51 times -2 is -102. And add up that column, I get -92. And if you want to check it on the calculator using direct substitution, you're more than welcome to, but I'm just going to move on. Okay, so for number 3, once again, I kind of set up this little L-shaped thing to keep it organized. I notice I'm missing an x squared in here. So I know I'm going to have to put that 0 placeholder in for the x squared. And just remember, anytime you have these positives and negatives in front of your x's, those are really 1s, right? So this is a -1 for the x to the 4th, +1 for x cubed, 0 for x squared, -1 for the x, and +1 for the constant. This -3 goes on the outside. Now I start my little pattern, dropping down that -1, multiplying the -1 to the -3 is +3, adding up that next column. 4 times -3 is -12, adding up that column. -12 times -3 is +36, add up the next column. 35 times -3 is -105. Add up that column, and I finish up with -104. All right, and we're going to do one more of these. Okay. So all my coefficients, I have 2, 1, -3, 5, and this time the missing thing is the constant. So we're just going to put a 0 in for that constant. So when I put my numbers in, I have 2, 1, -3, and 5, but because we're missing the constant, we're going to put a 0 in at the end because we need that one extra column. Then the x equals -1 goes on the outside, and then we start our process. Dropping down the 1, 2 times -1 is -2, adding up that next column. -1 times -1 is +1, adding up that column. -2 times -1 is +2, adding up that column. 7 times -1 is -7, adding that up, and we get -7. Okay, so now we're going to move on to the end behavior of polynomial functions. So graphs of polynomial functions, we can describe their end behavior. And what I'm talking about there is every graph you have two arrows on the two ends, and there's one arrow on the right side of the graph somewhere and one arrow on the left side of the graph somewhere. So we want to know, well, where are they going? Are they kind of going in an upward trend, or are they going in a downward trend? So it says the end behavior of a graph is going to describe the far left, which we refer to the left side of the graph as x approaching -infinity. And then we're also going to look at the end behavior of the far right side of the graph, which is written as x approaching +infinity. Okay, so if you think about an x and y axis, and we talked about this a little bit with domain and range yesterday, if this is the x-axis, this side would be going towards +infinity, and the left side would be going towards -infinity. So that's what we're talking about, the far left and the far right. And then, of course, your y-axis, this is where your function is going to be heading up or down as you go left or right. So if it's kind of heading in an upward trend, you'd say it's approaching +infinity. If it's kind of doing a downward trend, you're going to say it's approaching -infinity. And these things are going to be determined by the function's degree and also its leading coefficient. So I will get into that in just a minute. So first, I'm just going to kind of like show you what the end behavior looks like for a couple of these, and then we will go through how to identify it without the graph. So this first option here, so there's 4 types of end behavior. So this first option here, which says f of x approaches positive infinity as x approaches -infinity, and then it says f of x approaches positive infinity as x approaches positive infinity. You might be saying, what the heck? That looks like a whole bunch of gibberish, right? Well, remember from the top part, as x approaches -infinity, that is basically a fancy way to say the left side of my graph. This is the left side over here. As x approaches positive infinity, so that's this side, that's basically just saying the right side of my graph. So what's happening to the two sides of my graph? So let's do this one first for an example. Now, let's go over how we're going to do this. So because I see this lead coefficient here, and I also have an exponent, right? So this end behavior is determined by the function's degree and leading coefficient, which is really important when we put it in standard form, because we also use that leading coefficient and degree to determine like what type of polynomial it is and all of that. So the leading coefficient okay, determines the right side of your graph. All right, so it's going to tell you what the right side of your graph is going to do. So that's this one here. This is going to be determined by the lead coefficient. And basically what you're going to have two choices. If that leading coefficient is positive, your graph is, the right side of your graph is going to go up. If your leading coefficient is negative, the right side of your graph is going to go down. Okay, now remember, if it's going up, you're going to say it's approaching positive infinity. If it's going down, it's approaching negative infinity. That's like the fancy way that we write that. Now, if you think about it, this makes sense because this lead coefficient here on the parabolas that we were graphing was our A value. And remember when we would say if A was positive, the graph opens up. If A was negative, the parabola opened down. So that whole little thing that we talked about with the parabolas applies to all polynomials, but just on the right side. So for parabolas, it happens to apply to just the entire graph, so both ends, the left and the right. And I'll explain why that is in a minute. But with all other graphs, cubic, graphs that raise to the fourth, fifth, sixth, seventh degree, whatever, it's always going to be determining the right side no matter what. Sometimes it'll determine the left side as well, but it's always 100% of the time going to determine the right side. Is it going up or down? So anytime that lead coefficient is positive, the right side of your graph goes up. Anytime your lead coefficient is negative, the right side of your graph is going to go down. Okay, so then let's talk about how we determine the left side. So that's going to be the degree. So the degree is going to determine your left side. So if your degree is an even number, okay, the left side of your graph is going to do the same as the right. If your degree is an odd number, like 1, 3, 5, 7, 9, then your graph is going to do the opposite as the right. Okay, so we have to determine the right side first using the leading coefficient. And then after we've determined the right side, we use the degree to determine the left side. Is it the same or different, same or opposite as the right? Okay, so let's take a look at this first one here. So if I'm looking at this problem here in the green, okay, I know that my leading coefficient here is positive 3. So that tells me that my right side of the graph here is going to go up because it's positive. It's a positive 3. Now my exponent is an even number, so the left side is going to do the exact same thing as the right because they're going to be even, and it's also going to go up. And when we write it in the notation, this little space here that you'll be filling in, of course, you'll write positive infinity. So this graph would look something like this, where both sides are going up. Okay? So now another example for one like this would be x to the 8th power, 1x to the 8th. So again, the right side here is a positive, so the right side's going to go up. The left side is determined by this exponent, which is an even exponent. So it's going to do the same thing as the right, and it's also going to go up. So we would know that our end behavior for this graph here is also going to have two arrows pointing up. Now, because it's x to the 8th, that just has to do with how many times you're going to have like a dip or a minimum or a maximum in there. So I'm just estimating that right now. That's not so important just yet, but it's just the end behavior that we really want to focus on. Okay, so now let's take a look at the next example. Okay, so this is another problem. Again, all this notation is all the same for all 4 of these. The only thing that's different is where are the two y's going? Like is the left side is going down, up, or whatever. So again, x approaching negative infinity is left side of my graph. X approaching positive infinity is the right side of my graph, and we want to know what is the graph doing on each of those sides. Okay, so if I take a look at this problem here, and we don't need to draw these every time, okay? I don't need to draw that. I just need to determine what is the left side going to do and what is the right side going to do, right? So my leading coefficient determines the right side. Since it's a negative, the right side is going to go down. My exponent, however, is even, which means it's going to do the same as the right, so it's also going to go down. And that's why these two infinities in here are both negative infinities. All right, so let's try this example here now. So this one here, what's the left going to do? What's the right going to do? Negative a value, so the right side is going to go down. And even exponent, so the left side's going to do the same thing and also go down. And then, of course, we would write that in there. Now, if you wanted to see, like a lot of times the purpose of doing this is so we kind of have an idea of what this graph would look like without actually graphing it. So this first one here, we know that both ends are going to go down, right? So it would probably look something like this because it's x to the fourth. That's how I know how many turns it has, which we'll learn in a couple sections. This one here, still down and down, just x to the 6, so it's going to have an extra little curve, that's all. But that's not important just yet. All right, let's try two more. Now notice this time, again, everything here is the same in this notation. The only thing is different is where's the f of x approaching, and that's what you have to answer. That's the part you need to figure out. Everything else is just formality. Okay, so this is the left side, this is the right side. This is the left side, negative infinity, this is the right side. So as x approaches negative infinity, that's just saying what's the graph doing when it's on the left? As x approaches positive infinity, what's the graph doing on the right? So if we look at this one first, right here, okay, what is happening on each side? Positive leading coefficient, the right side's going up. Now, if you don't see an exponent there, that really means it's a 1, which is an odd number. So the left side has to do the opposite of the right, which in this case would be go down. So if I were to draw this graph, I would expect that the right side would be up and the left side would be down. And I know it's linear, so I just graphed a line. So now let's try the next one. What's the left going to do? What's the right going to do? Okay, positive leading coefficient, the right side's going up. Odd exponent, the left side's doing the opposite, so it's going to go down. So if I were to graph this one, I know the right side is up, the left side is down. It would probably go something like that. And these are just rough sketches. It's probably not exact, but you get the idea. And notice left down, negative infinity. Right up, positive infinity. Left down, negative infinity. Right up, positive infinity. All right, we're going to do one more. Okay, so this one here, negative leading coefficient right there tells me my right side is going down. Odd exponent means the left's going to do the opposite and go up. So if I were to draw that one, and this one's cubic, so I know the left is up, the right is down, and this one will have like one curve in there. And then finally, this last one here, my right side is going to be down because the leading coefficient is negative. My left side is going to have to do the opposite because my exponent is odd, so the opposite of down is up. If I were to graph this one has that 9, so there's a lot of little turns in there, but left up, right down is the main thing, and then you're doing 1. I think it's something like that. All right, so hopefully you understand how to identify that end behavior and what it kind of is referring to. So now on the next page, we're going to identify this end behavior for every problem, and then we're going to use the graphing calculator to actually graph it and get a sketch. Now we're going to use that notation so we can practice with that notation that we were just doing for every one. So for every one, the first thing we're going to do is find the end behavior. And I'm going to write it in the notation so that you can get practice filling in the notation. Now this part that I'm writing here in the black is going to be the same for every single problem because this part does not change. That's just the notation to describe the end behavior. So if I said to you describe the end behavior, that should be written and you would just fill in those two blanks with either positive or negative infinity depending on what your graph or equation is telling you. Remember, x approaching negative infinity is the left side. X approaching positive infinity is the right side. So this is the right side over here. X approaching positive infinity. This is your left side over here where x is approaching negative infinity, right? So looking at the lead term in my equation, I don't even need to graph it to know what the graph's going to do. Because right away, I know that the right side of my graph, since this is a negative leading coefficient, it's going to go down, which means f of x is going to approach negative infinity on the y-axis. Then I have to do the left side, so I'm going to look at my exponent. My exponent is an odd number, so I'm going to do the opposite of the right. So since my right went down, my left is going to go up, which means it's going to approach positive infinity. So that's the hard part, the end behavior. Then on the chart, I'm just going to go ahead for every problem and fill in -2, -1, 0, 1, and 2 for my x's, and I'm going to do this on my calculator, okay? So on your graphing calculator, and just as a little refresher here, I'm going to do second plus sign to reset my calculator. So I'm going to go number 7. Either of those options is fine. I'm going to go to all RAM, reset. And I'm also going to reset my screen here, so if you want to look and see what keys I'm hitting, you can tell. Now to graph anything, we go to y equals, and we just type it in as it's written. Now you have a negative x to the third power, so you want to use your negative x raised to 3, arrow over to get out of the exponent, and then plus 2. When you hit graph, you get a little visual. You should be able to visually check that end behavior. The left side is going up or approaching positive infinity. The right side's going down or approaching negative infinity. Now when you go to second, which is like a shift key, and then hit graph again, you get your table, arrow up if needed to get some of those negatives, and we're going to fill in the y values that correspond to the -2, -1, 0, 1, and 2. So we have 10, 3, 2, 1, -6. 10, 3, 2, 1, and -6. And now we're just going to plot whatever fits on our graph. So -1 and 3 fits, 0, 2, 1, 1, and 2, -6. And we know that there'd be something else way up here. And then making sure your end behavior that's expected, left up, right down, is what you're getting on your graph. Okay, so now we're going to go down and do the other ones. All right, so first thing we want to do is our end behavior. So we're looking at this term here. I'm just going to write out the notation that you have to fill in. So f of x approaches blank as x approaches negative infinity. And then the other side, f of x approaches blank as x approaches positive infinity. And once again, x approaching positive infinity is the right side. X approaching negative infinity over here is the left side, right? Because this is the x-axis approaching negative infinity. Okay, so now looking at this first term that I highlighted, we can figure out what the end behavior is going to be. So the right side is determined by this lead coefficient. Since it's a positive number, we know my right side is going up, which means it's approaching positive infinity. Then the left side, we have to look at our exponent. The exponent is odd, which means that's a little bit different or opposite of the right. So it's going to go down, which means it's approaching negative infinity. Now I'm just going to fill in -2, -1, 0, 1, and 2. I'm going to get numbers to do this graph from my graphing calculator. Now, when you go to your y equals, I would recommend you just clear out the last graph because you no longer need that. Type it in as it's written on your paper. So 2x raised to the third power minus 3x minus 1. Graph it to get the visual. Make sure your end behavior is what you predicted. Left down, right up. Looks good so far. Going to my table of values to fill in those numbers. So I have negative 11, 0, negative 1, negative 2, 9. Negative 11, 0, negative 1, negative 2, and 9. Just double check. Good. So negative 2 and negative 11 doesn't fit. Negative 1, 0, 0, negative 1, 1, negative 2, and then 2, 1, 2, 9. Now, without knowing the end behavior, we're seeing the graph in the calculator be really hard to graph this because we know that the left's going to go down. So we know once we get to this point here, it's going to kind of dip back down. And it'll look something like that. It just has to be a rough sketch. It doesn't have to be like perfect. Just make sure that it's the end behavior is definitely what needs to be correct. Okay, number 3. Start out with that end behavior. Okay, so we know that the right side is when x is approaching positive infinity. That's the right side. The left side, whoops, is when x is approaching negative infinity, right? So let's look at this first term. It's already in standard form, so it's just that first term there. The lead coefficient determines my right side. The lead coefficient is a negative, which means my right side is going to go down or approach negative infinity. Then I want to do my left side, so I look at the exponent. Since it's an even exponent, my left side is going to do the same thing. It wants to be even or the same as the right side. It's also going to go down, and that's also going to approach negative infinity. Then I go to my calculator to check my visual graph to see that I did that end behavior correctly. So negative x raised to the fourth power plus 5x to the second power plus 2x, graph it. Okay, again, down on both sides, which is what we expected. Get some points on my table, 0, 2, 0, 6, 8. 0, 2, 0, 6, 8. And of course, that's just for the negative 2, negative 1, 0, 1, and 2 again. So negative 2 and 0, negative 1 and 2, 0, 0, 1 and 6, 2 and 8. And just make sure that your end behavior kind of matches up to what you expect. Now, a lot of people might say, well, why wouldn't I just put everything in the calculator and see my end behavior? Well, that's fine, but sometimes the numbers in your graph could be like ridiculous numbers that won't really show up on your calculator. So for example, let's say you had like, x to the 257th power, something ridiculous. To try to graph that and be able to see it on your graphing calculator would be very, very difficult. So that would be an example where you wouldn't be able to graph it to see what it's going to look like. And aside from that, it just wastes time. So if you're taking a test or something and you can answer the question just by looking at the equation rather than having to go through the process of graphing, that will also save you a lot of time. All right, so the last 3. Now these 3, the graphs will not have as many twists and turns as the previous ones, even though the exponents are larger. And that's because sometimes some of those x intercepts and whatnot are actually imaginary numbers. So when the intercepts are imaginary numbers, we can't physically see them. So in case you're wondering why the graphs look a little silly on these 3. Okay, so again, though, the end behavior does not change regardless. So I'm just simply putting in that notation for every single one. It's the same exact notation. You just have to fill in where the f of x is approaching. Okay, so once again, the right side, x is approaching positive infinity. That's the right side. The left side of our graph, x is approaching negative infinity, right? So then we look at that lead term to determine what each side is doing. Positive leading coefficient, +1, so we know the right side's going to go up, right? And that would mean it's approaching positive infinity. The left side of our graph over here is based off of this even exponent telling us that the left and the right are going to be the same or even. So the left side's also going to go up since the right went up. So it's also approaching positive infinity. So now we're just going to look up the points on our calculator for this graph. So again, go to y equals, clear out what's in there. We're just going to go do x raised to the 6th power plus 2. Graph it so you can kind of see the two end behaviors both going up. Go to your table, second graph, and I'm going to write 66, 3, 2, 3, 66. Clearly, the 66s are not going to fit on our graph, so I'm just going to plot the 3 points that will fit. So -1 and 3, 0 and 2, +1 and 3, and then we know that the ends are both going up. All right, so we've got 2 more left in this lesson, and then hopefully you guys are good. So again, I'm just writing out that notation for the end behavior. It's the same thing. Hopefully after I do it 6 times, you guys will be good with it. Okay, once again, x approaching positive infinity, that is the right side of your graph. X approaching negative infinity, that is the left side of your graph. We're going to look at this lead term here and determine what is the right side doing, what is the left side doing. So first we look at that lead coefficient, which is negative. That tells us the right side is going down or approaching negative infinity. Then we look at the exponent. It's odd in this case, which means the left side is going to do the opposite of the right, which would be going up or approaching positive infinity. So the left side is going to go up and the right side here is going to go down. And then we're going to just get those points off of our graphing calculator and see what this graph kind of looks like. So once again, y equals, clear out the graph that's in there. We no longer need that. Negative x raised to the 5th power minus x plus 3. Graph it. We can see that end behavior shaping out there. And then we're going to go to our table, 37, 5, 3, 1, negative 31. So plotting what I can fit, which looks like it's just going to be the -1 and 5, 0, 3, and 1, 1. Now, of course, that looks like it's graphing a line, but we know better than that, right? We know that it's going to actually kind of curve after it goes through those 3 points. So that's why it's really important to know, more than just 3 points sometimes, especially with cubic functions or things like that. Okay, one more. First thing, our end behavior. Let's figure out what that end behavior is. Okay, the right side of our graph is x approaching positive infinity. The left side of our graph is x approaching negative infinity. Looking at this lead term here, the right side is a positive leading coefficient, so the right side is going to go up or approach positive infinity. And that even exponent tells us the left is going to do the same as the right and also go up. And then lastly, I'm just going to graph this one by putting it in my calculator. Y equals, clear out your old graph, 2x to the 4th power minus 6x plus 2. And we're going to graph it. It kind of looks like a lopsided parabola. Then we're going to get our points. Okay, so 46, 10, 2. 46, 10 to -2, and then the next one was 22. All right. -110, 0, 2, 1, -2. And if you kind of look at the graph, it might be a little hard to see, like, how are these connecting here? But that point down there looks like it's the minimum. So we know it's kind of coming through. Sorry, that was a little crooked, and then going up like that. So rough sketch. All right. So that concludes our lesson on evaluating and graphing polynomial functions and discussing that behavior.